For 2 centuries, Isaac Newton's laws of mechanics defined our reality. This framework treated space as a fixed, unmoving stage, and it treated time as a universal, absolute clock. It ticked at a constant rate for every observer in the universe. By the late 19th century, experimental evidence confirmed that light behaves as a wave. In the classical view, every wave requires a physical medium to travel through, just as sound waves move through air and ripples move across the surface of a pond. Physicists hypothesized that this medium was the luminiferous ether, an invisible substance that remained at rest relative to the stars, while the Earth traveled through it during its orbit. Detecting this motion was the expected confirmation for the mechanical universe, verifying that every wave in existence traveled through a tangible, universal background. In 1887, Albert Michelson and Edward Morley designed an experiment to measure this ether wind, the drag created by Earth's movement through space. They utilized a sensitive instrument called an interferometer to split a light beam and send the resulting beams in perpendicular directions. They expected to find that light traveling against the ether's flow would move slower than light traveling across it. Instead, the two physicists recorded a null result. Light traveled at the exact same velocity, regardless of the Earth's orbit, the direction of the beam, or the motion of the source. This result completely dismantled the entire ether paradigm. It proved that light did not require a medium, and that its speed remained constant, violating the core rules of classical physics. This created a conflict with the basic definition of speed as distance divided by time. To keep the speed of light constant for every observer, the measurements of distance and time themselves had to become variable. In 1905, Albert Einstein adopted a principal theory approach. He set aside unproven mechanisms like the ether to rebuild the laws of physics entirely from verified empirical facts. He established two postulates. The laws of physics are identical for all observers, and the speed of light is an absolute constant. This forces a trade-off. Space and time must bend and stretch to ensure everyone measures the same light velocity. This unified space and time into a single four-dimensional entity known as spacetime, where the two are permanently interwoven. This leads to specific measurable effects. Moving clocks are measured to tick more slowly than an observer's stationary clock, and objects are measured to shorten in the direction they are moving. Special relativity successfully explained the behavior of light and motion, but it was incomplete. It only applied in the absence of gravity. Einstein spent the next decade integrating gravity, beginning with the equivalence principle. He realized that a person in a falling elevator experiences the same physical reality as someone floating in deep space. This proved that free fall is actually inertial motion. Objects in free fall are simply following the path of least resistance when no other forces are acting upon them. Einstein's 1915 theory of general relativity describes spacetime as a flexible geometric fabric. Massive objects like stars and planets physically distort this fabric, creating curves in the four-dimensional universe. Planets maintain their orbits by following the natural curvature of this spacetime fabric. Gravity exists as the geometric consequence of mass warping the universe, dictating how objects move through space and time. Testing this radical model required finding astronomical anomalies that Newtonian mathematics could not explain. Mercury provided the first proof. Its orbit featured a slight, unexplained wobble that general relativity calculated with perfect accuracy. The theory also predicted gravitational lensing, where the mass of a star or galaxy physically bends rays of light passing nearby, a phenomenon confirmed by observations during a solar eclipse. Relativity further predicted the existence of gravitational waves and phenomena like singularities, where the curvature of spacetime becomes infinite. These theoretical milestones gave birth to modern astrophysics, leading directly to the identification and eventual imaging of black holes. Beyond deep space, relativistic effects are tangible constraints on modern technology. Global positioning systems must constantly adjust for kinematic time dilation, because satellites move at high speeds relative to Earth, causing their onboard clocks to tick slower. Simultaneously, those satellites sit further away from Earth's center of mass, meaning they experience weaker gravity, and their clocks tick faster due to gravitational time dilation. If engineers ignored these calculations, GPS navigation would drift by kilometers every day, and instruments like electron microscopes and particle accelerators would cease to function. Einstein mapped the hidden operating code of our universe, proving that reality is infinitely more fluid and interwoven than our senses perceive.